In this lesson, we're going to talk about phase separation and critical points. If you recall, back in the early part of the module, we discussed a critical point with respect to a material like either water or CO2. In this particular case, if we plot the pressure and the volume together, what we find in the liquid vapor phase field, a point where we have two phases in equilibrium, and as the temperature goes up, what we find is the volume of the two phases become closer and closer to one another until we reach the temperature at which those two phases appear to be virtually identical with respect to their volume. And we refer to this point as a critical point. Now we have something very similar with respect to the monotectic. In this case, what we have is our region of two-phase miscibility, which is given there by that dome. And what we're going to do is we're going to look at several compositions. We're going to look at a composition at a particular temperature for each of the three phases that are in equilibrium with one another at that temperature. So then what we're going to do is to increase the temperature for that particular composition. That composition we're going to call the critical composition. So as we go up in temperature, by the indications of the red lines, what's happening in this particular case is those two compositions are coming close together, much like what we had in the case of liquid vapor phase critical point. Now we have the same thing here, except it's liquid-liquid. Again, what we're doing is we're plotting an intensive variable, which is either pressure on the left or temperature that's on the right, and we're plotting it against extensive variable, namely we're looking at the volume in one case and the composition in the other case. Now, we have something very similar with respect to solids. We're looking at a congruently melting minimum, and you can see that in the upper portion of the diagram. Remember, the liquidus and the solidus come together at that congruently melting minimum point. But what we see, and has been introduced in this diagram, is a miscibility gap. What this miscibility gap is the fact that we have two solids of the same crystal structure, except they have two different compositions. And we're going to just identify those as alpha 1 and alpha 2. Now, if we choose a particular temperature and when so that we are inside of that two-phase field, what we have is on the left-hand side we have the composition of alpha 1, and on the right-hand side we have the composition of alpha 2. So we read those compositions down all along the x-axis. So we're in that particular phase field, and now what we're going to do is we're going to increase the temperature. And as we increase the temperature, what we begin to see is the compositions of those two solids come very close together, and then eventually at the critical temperature, what we find is we have precisely the same composition with respect to the alpha phase as the alloy comes out of that two-phase field. And again, this is a critical temperature. So we've seen examples of this phenomenon of a critical temperature in liquid vapor, in liquid-liquid, and now in terms of solid-solid. I would like to turn our attention here for just a moment to talk a little bit about liquid phase separation in polymer blends. Now, as it turns out, there are 5 types of phase diagrams that we often see with respect to polymer blends. These are schematic representations, and what we have with respect to these different phase diagrams is we have a region of two-phase equilibrium, which is always surrounded by regions of single-phase fields. And so in each one of those diagrams, we'll see regions of two-phase equilibrium, and we'll see regions of single-phase equilibrium. And in many regards, for example, if we look at the diagram on the bottom row, the one to the left, where we have on either side of this region of two-phase equilibrium, we have two single phases. That portion of this diagram looks much like what we saw for the liquid-liquid separation in the monotectic and also the solid-solid. So again, we have a single phase on either side, and we have two liquids on the interior. Now, the thing that becomes important is, if we look at each one of these diagrams again, we're going to see an interesting point on the diagrams. In the first case, we're going to see something that is a critical point, but it has a specific designation when we talk about polymer systems. In this case, it's referred to as an upper critical solution temperature. That is, the critical point is elevated, and it represents a maximum in terms of the temperature at which the critical phenomenon occurs. And there are two diagrams in here which behave that way. The one up in the middle on the first row, and the second row, the one over to the left. In addition to having an upper critical solution temperature, we're going to see that we also have a lower critical solution temperature. And so what we see here are minimums as opposed to maximums. So again, we have this phenomenon with respect to criticality in the polymer blends. And so I wanted to bring all of these together because they do show a trend and they appear in all of the different material systems. Thank you.